In this lesson, you will learn what makes an object float and how to do simple calculations of displacement and draft. Also covered in this lesson are the definition and derivation of kips per inch immersion. With the KPI values, you can simplify calculations of displacement and draft.
The two suspended objects are to be dropped into the water. Review the weight, W, and volume, V of each object. Now we click on the block to release it.
Although the weight of the two objects is the same, the barge floats and the block sinks. Because the submerged volume of the barge is larger than the total volume of the block, the volume of water displaced by the barge is greater than the one displaced by the block. And the upthrust force which keeps the barge afloat, called also the buoyancy force, is the weight of the volume of the water displaced by the barge. The barge floats because it displaced its own weight of water before being completely submerged. The block sinks because its volume is not large enough to displace its own weight of water before being completely submerged.
Given the following properties of a body to be placed in seawater, which one will determine whether the body will float or sink? A, the body weight. B, the body shape. C, the body volume. D, the body weight and volume.
Archimedes' principle states that when an object is immersed in a fluid, the object experiences an upthrust force equal to the weight of the displaced fluid. Once the weight of the displaced fluid and the original weight in the air of the object are equal, the object will neither fall nor rise in the fluid. Its apparent weight in the fluid is zero. As long as the weight of the displaced fluid is smaller than the weight of the object in the air, the object will fall, sink in the fluid. Its apparent weight in the fluid is greater than zero.
Next, we perform an experiment illustrating the Archimedes principle. Given a solid block, dimensions, height equals 5.0 feet, width equals 10.0 feet, length equals 21.0 feet. The block weight in air equals 40,320 pounds. Container filled with seawater and drainage to an empty container placed on a scale. Now we lower the block into the seawater until the block is freely floating.
The freely floating block has experienced an apparent loss of its whole weight.
Submerged volume is 630 cubic feet. How many cubic feet of water were drained into the empty container? Now we repeat the experiment with a smaller block. Given a solid block dimensions, height equals 5 feet, width equals 4 feet, length equals 21 feet. The block weight in air equals 40,320 pounds. Note, in this experiment, the block weight in air is the same as in the previous one, but the block width has been reduced from 10 feet to 4 feet. Let's see what happened after lowering the block.
The sinking block has experienced an apparent loss of just part of its weight. The weight of the block after it submerges is equal to its original weight less the weight of the displaced water.
The submerged volume is 420 cubic feet. How many cubic feet of water were drained into the empty container? The correct answer is 420 cubic feet. The volume of displaced water is the same as the volume of the submerged block. The block weight in air is 40,320 pounds, and its submerged weight is 13,440 pounds. How heavy should the weight be to balance the water-filled container? The correct answer is 40,320 pounds minus 13,400 pounds equals 26,880 pounds. It is the weight of the block in air less its weight in the water.
The weight of an object in fluid is equal to the object's original weight in air, less the weight of the fluid displaced by the object. When a partially submerged object is floating freely, its original weight in the air is equal to the buoyancy force, which is the weight of the fluid displaced by the submerged part of the object. The weight of the displaced fluid is called displacement. It is equal to the volume of the displaced fluid times its density. The density, d, of any liquid or material is the ratio between its weight, W, and its volume, V.
In the following experiment, we'll show how to determine the density of liquid. First, find the weight of the container. Second, zero out the weight of the container, 10 pounds. Now we fill 1 cubic foot of seawater to check the density. The density of the seawater is Next experiment, now find the density of the empty container. The weight of the empty container is 10 pounds, and the volume of its material is 1.6 cubic feet. Find the density of this container. Use W divided by V to find the density of the container. The answer is 10 pounds divided by 1.6 cubic feet equals 6.25 pounds per cubic feet.
The specific gravity, Sg, of a liquid or any other material is defined by the following ratio.
The density of fresh water is 62.4 pounds per cubic foot. What is its specific gravity? The density of seawater is 64 pounds per cubic foot. What is its specific gravity? The density of diesel oil is 53.5 pounds per cubic foot. What is its specific gravity? In doing stability calculations, the following designations are common. To help you remember the difference between these two, notice that the symbol for volume is shaped like a V. For a floating object, the volume of displaced water is equal to the immersed volume, V, of the object. The weight of water displaced by a floating object is equal to the weight of the object.
Note that in this course, the weight of the floating unit is designated also as displacement.
Review the above information, then pause this video to calculate the displacement of the block shown floating in seawater.
The displacement of jack-up units is measured in either tons or kips. Throughout this course, we will use the kips unit for weight and displacement. 1 kip is equal to 1,000 pounds. The daily stability calculation for floating units requires that you determine the draft, D. Draft for box-shaped floating unit may be found knowing its weight, W, and dimensions, where beam, B, is the width of the box, and length, L, is the length of the box.
Now we review the steps of draft calculations. Step 1. Convert the weight into volume. V equals W divided by D. Step 2. Convert the volume V by water plane area, B times L, to get the draft D.
Draft change effects on displacements.
Often, you will need to ballast the unit to different drafts. This barge is required to be ballasted down from a draft of 20 feet to 21 feet. Now, we will ballast the barge to 21 feet.
KPI and KPF definition.
We have increased the barge draft by 1 foot, and the corresponding increase in the barge's weight is 1,344 kips. Because of the barge's straight rectangular shape, any change in 1 foot in draft along the depth will generate a weight change of 1,344 kips. This change of weight per 1 foot of change in draft is a useful quantity called kips per foot, KPF immersion. Thus, the KPF for this particular barge is 1,344 kips per foot. Another term more frequently used than KPF is kips per inch, KPI immersion. To convert KPF to KPI, just divide by 12 as follows.
The KPF, or KPI of a barge, is calculated as follows. Let's pull out the section of the barge that was submerged when we ballasted down from 20 feet to 21 feet.
Sample calculations using KPI. Ballasting calculation using KPI. Practice. The KPI of the barge is a constant 140 kips per inch, and its present draft is 16 feet 8 inches. You are required to deballast the barge to a draft of 16 feet. What is the ballast weight you should discharge from the barge?